All right, IBSL1. Today's the big day. We finally talk about everybody's favorite math word, logarithms. So pumped. Logarithm is going to get you. That's a reference to an old Paula Abdul song for all you Paula Abdul fans out there. You guys, first, before we talk about what logarithms are, you have to realize that they're so closely connected to exponential functions. So here, exponential a to the power of x. Exponential functions and logarithmic functions, I sometimes call them cousins because they are inverses of each other. See that f to the negative 1 right there? So that means if f of x is equal to a to the power of x, then the inverse of that is log base a to the power of x. That's a base right there. That's how you say that. Log base a of x. So, very quickly, we're going to touch on what the graph of a logarithm looks like. Remember that the exponential graph looks like Superman taking off. So it's got his horizontal asymptote, a runway, stays close to the runway, and then really takes off after the y-axis crosses at 0, 1. Now, remember that inverses are just reflections over this line y is equal to x. So if you take that and fold it over the dotted line, you get not Superman, but what I like to call Mole Man. Now, here's the way Mole Man works. Mole Man starts at the center of the Earth and then comes all the way up and then bursts through the surface right here at 1, 0 and then flies. Mole Man, instead of a horizontal asymptote, has a vertical asymptote that is the y-axis. So instead of a runway along the x-axis, Mole Man's got a runway on the y-axis. So this is y is equal to log base a of x. The domain of that, well, notice that it doesn't exist anywhere over here. It only starts to exist just after the y-axis. So the domain is going to be negative infinity. Nope. Come on, Jolly. Starts at 0, doesn't include 0, goes up to positive infinity. So that's the domain of this, y equals log base a of x. The range goes forever up and down. Like Mole Man keeps flying forever up into the air. So it's going to be negative infinity to positive infinity. Please notice that this is a switcheroo of the domain and range of Superman. Superman's domain is negative infinity to positive infinity, but the range is limited from 0 up to positive infinity. Remember that with inverses, everything switches, including the domain and range. All right, we're going to take this function, log base 10 of x minus 2 plus 1. You guys, anytime you see some extra things being added into functions, remember that these are just transformations that work the same way that they always do. Like this minus 2 is pushing it to the right 2. This plus 1 is pushing it up 1. So that's the first thing we're going to do is describe those transformations. So the parent function, not parrot function, went translated right 2. And also translated 1 up. Now we're going to sketch it. So we're going to sketch f of x and its inverse on the same graph. So I think we should start with the Mole Man graph because we know it's like a parent Mole Man graph that's gone to the right 2 and up 1. So normally the Mole Man would come up from here and cross at 1 and then start flying. But we're going to go to the right 2 and up 1 with that. So it's like it goes, this point right here goes to the right 2 and up 1. So we know that this is on the curve. And we know that the horizontal, well, I should get rid of the original. Oh no, I have to, oh no, Jolly, what have you done? Maybe I'll keep it in. We know it goes to the right 2 and up 1, which means that the vertical asymptote also gets shifted. So we'll do a different color for this one. So that got shifted to the right 2. So the vertical asymptote is now here. So Mole Man comes up and then doesn't bust through the surface, but busts through right here at the point 1, 2, 3, 1. Because normally it would be 1, 0, and it went to the right 2 and up 1. So 2, 3. Yep, that works. Now we also had, so that's mole man. That's f of x. But then we have to sketch the inverse of that. Remember, if the point 3, 1 is on the curve, that if you swap that, that means the point 1, 3 is on the other curve. So if I go over 1, up 1, 2, 3, that means that it crosses there. Now, mole man's runway is here at x equals 2. So that means Superman's runway is going to be y equals 2. So it would look something like this. Hey, you guys, do those two lines look like reflections of each other over the line y is equal to x? Sure does, Jolly. Nice work, as usual. I'm sorry. You guys, the domain of f of x. So f of x is just mole man here. It starts at 2 and goes up to infinity. So that's going to be 2 up to positive infinity. The range is going to be all real numbers because it goes forever down and forever up. And the equation of the asymptote of f is going to be x is equal to 2. Good problem. Now, you guys, everybody is so afraid of logarithms, but I really think this is your biggest tool when it comes to logarithms. I call it spiraling. So let's start with this log right here. Log base a of c equals b. So that's like the base. You say log base a, and then this part right here is called the argument. So you say log base a of c. Here comes the spiral. If you want to think, every log, because it's a cousin of an exponential, can be put into exponential form. And here's how you spiral. You always start with the base a, and then you jump the equal sign over to the other side, and then you spiral back across the equal sign to the argument. So an equivalent way to say this is a to the, so this is the to the part, b is equal to, and you know it's equal to because it jumps over to the equal sign. So we'll say equal to right here. So a to the b is equal to c. This is called logarithmic form. Logarithmic in my top 5 math words. Not 1, 2, or 3, but it's up there somewhere. Any logarithmic form can be changed into exponential form. So, a lot of times if I'm given a log, I'll sometimes think about the spiral relationship, and that can help you with the problem, depending on what you're trying to do. Other times, it might make more sense to take the exponential form and try to turn it into the logarithmic form. So, I want to emphasize that you guys should be able to go back and forth between these. Sometimes it's better to have it in logarithmic. Sometimes it's better to have it in exponential. Couple special ones that the book wants me to talk about. I think they're kind of, well, I wouldn't say obvious, but I think they're figure-outable if you just know your spirals. So if you think like, okay, I don't know what log base a of 1 is equal to. Just think about the spiral. A to the something is equal to 1. So the exponential form would be a to the what is equal to 1. Well, you guys, how do you raise something to a power and get 1 out of it? The only way to do that is that if it's 0. So log base a of 1 is equal to 0. Similarly here, if you think about, okay, a to the what is equal to a. So this is like a to the question mark is equal to a. Well, a to what power gives you a? The only way to do that is with 1. Last one, this is the funniest one if you spiral it. If you think a to the what gives you a to the x, so it's like a to gives me a to x. Well, what is it? It's like a to the x equals a to the x. You just have to say it out loud. So this one equals x. The other way to think of that is that If these guys are matchy-matchy, you can sort of cancel out all this and it would just be x. First example, write log base 7 of x equal to 2 in exponential form. Well, just spiral that puppy. 7 to the power of 2 equals x. So 7 squared is equal to x. Now, a lot of you might look at that and be like, we should change the 7 squared into 49, but the directions are always so important. It just says write it in exponential form. And you know what? I've done that, so we're good. And I'll box my answer because Railsback started boxing her answers because I did it once. So we'll all start boxing our answers. That's cool. Next one. Write x equals root 25 in logarithmic form. This might be weird because a lot of you will really want to turn this into 5. Don't do that. What you should actually do is remember that every square root or any root can be written as a rational fraction. So this, not turning it into logarithmic form yet, I'm just rewriting it as a fractional exponent. Then you can unspiral. And the way I always do this is think like log base something of something is equal to something. So the base, when you spiral, is going to be 25. So this is log base 25. Then you have to jump the equal sign to the power. So the power goes over here. And then this is of x. I always do a quick spiral on these to make sure I got it right. Like 25 to the 1/2 equals x. Oh yeah, that's the exact same as 25 to the 1/2 equals x. So we're good. We got it. We'll clean up here. That's in logarithmic form. Find the value of log base 2 of 32. Okay, here's how I think you guys should do these problems. Log base 2 of 32, let's say we don't know what it's equal to. And then you can just spiral this. 2 to the what equals 32. So 2 to the equals 32. Then you just need to be good at spotting those hot numbers that should jump out at you. 32 is a power of 2. This can be rewritten as 2 to the what equals 2 to the 5th. Then you can get rid of these guys and just say the is equal to 5. So back to my OG color. This whole thing, whoops, that's not an eraser. Log base 2 of 32 just reduces to 5. Like that is your answer. There's no equal sign. I used an equal sign to help me figure out what it is, but you shouldn't write like x equals 5 or question mark equals 5. It's just like when you reduce a fraction. Like if you were to reduce a fraction, you wouldn't introduce an equal sign, you just reduce it. So log base 2 of 32 is 5. All right, you guys, the laws of logarithms. These are also called properties in a lot of textbooks, but IB calls them laws. So the laws are going to be all on this side over here. The way I always remember them is by thinking about their exponent cousins. So exponent cousins say, let's use pink. If you have the same base over here of a to the x times a to the y, that you would add their exponents. So this is a to the x plus y. So please notice that the multiplication turned into addition. Now, it works the same way with your cousins over here. If you have multiplication between x and y, that means that you can break it apart into 2 logarithms that are being added. So, notice once again here that the multiplication turned into addition. The same way that multiplication turned into addition over here. Oops, I already filled in this one. Let's get rid of it just for the sake of the colors. If you have a to the x over a to the y, you would subtract their exponent. So this would be x minus y. It's the same thing over here, that if you had, so notice that the division turned into subtraction. This division also turns into subtraction. So log base a of numerator minus log base a of denominator. So division turns into subtraction. Power of a power, right here. What do you do when you have power of power? Well, you just multiply their powers. A to the xp. So the powers turned into a multiplication. It's the same thing over here, but it's kind of funny. So the way you want to view this guy is that if there's ever a power on the argument, yes, it turns into multiplication, but here's what happens. This p gets to come out front. Little p turns into a big P. So this becomes p log base x. Plogax. Oh, that one is a good one to know that it works both ways. Oh, actually, Jolly, come on. For all of these, they work both ways, which means sometimes it's advantageous to take a logarithm and break it apart into two. Other times, it's better to take the two logarithms and smush them back together. So I guess with all of these equal signs, we should be putting like a double arrow, because sometimes it's good to take the condensed version and expand it, and other times it's better to take the expanded version and condense it. Oh, the book wanted me to talk about this guy. There's some slick little proofs for why this is true, but I always just remember if this space matches this space, you can just get rid of all of it, and it's just x. That's it. So an example of that would be 2 log base 2 of 5 is equal to, well, this would be equal to 5 because the 2 log base 2's cancel out and leave you just with 5. All right, some actual examples. Write each as a single logarithm. So this is what I call smushing. We're going to take both these two logarithms and smush them together. So remember that multiplication breaks apart into addition, or conversely, addition smushes together into multiplication. So this is the same thing as log base 8 of 6 times 3. So our final answer would be log base 8 of 18. The one thing I would do in this case is think, is there a power of 8? If you say this is equal to, is there an 8 to some power that gives me 18? But that's not true. There's no power of 8 that is 18. So this is our final answer. This is simplified, reduced, whatever you want to say. Next one, we're going to smush a subtraction together. Remember that subtraction and division are linked together. So this, when you smush it, becomes log base 5 of 9 over 3, which means this is log base 5 of 3. Then think to yourself, is there any power of 5 that is equal to 3? No, not a nice one. Ooh, classic trick question. Smush these two logs together. But Mr. Jolly, this part isn't a log. Well, you know what? We can actually use the properties of logs to change that into a log base 7. So we won't touch the first log, but the second log can be written as log base 7 of 7, because 7 to the 1 is equal to 7. So I can change this one into a log base 7 of 7, because this is the same thing as 1. Then subtraction turns into division. So this becomes log base 7 of 6 over 7. Ooh, double trouble. Okay, there's two things I see that we're going to have to do. First up, this multiplier on the outside is going to have to go back up into a power spot. So the same way you can take powers and put them out front as multipliers, you can take multipliers and put them back up into power spots. The other thing is that this is not a log base 10. So I'm going to have to figure out how to turn that 2 into a log base 10. Here we go. First, I'm going to take the 2 and pop it back upstairs. So this becomes log base 10 of 5 squared. Now, this guy, I need to turn into log base 10. So let's do log base 10 of what would give me 2? Well, think if this is going to be equal to 2, 10 squared is 100. So this whole thing right here is 2, because 10 squared is 100. Now they have the same base. I'll do a quick cleanup. This is log base 25 plus log base 10 of 100. Then the addition between them can become multiplication. So we get log base 10 of 25 times hundo. So this is log base 10 of 25 hundo. Is there a power of 10 that you raise it to and you get a nice 2500? I don't believe so. You guys, apologize for a long video, but that's a lot of information about logarithms. You should have seen this stuff before, but hopefully it was a little less painful this time around. Good luck on the homework.